From the massive skyscrapers that shape our cities all the way down to the humble paperclip on your desk, steel is literally everywhere. It's kind of like this invisible giant, the silent hero holding up our entire modern world. And because it's so common, we almost never stop to think about it. So today, let's do just that. Let's follow the incredible journey of this material from a rock deep inside the earth all the way to the driver's seat of your car. And just to give you an idea of how much we lean on this stuff, get this. The average passenger car you see on the road has about 1,000 kilograms of steel in it. Yeah, that's a literal ton of metal that gets you from point A to point B, keeping you safe and sound. It's a pretty staggering amount when you really think about it. I mean, it doesn't just magically appear, right? The steel in your car, your house, your kitchen, it has been on an absolutely epic journey of fire, chemistry, and some seriously incredible engineering. So let's follow that journey. Let's start with a raw rock and see how it becomes a finished high-tech product. Right, our world of steel. It's in everything from bridges to forks. And before we even get into how it's made, it's just worth remembering that this one material is what made everything from the Iron Age to the Industrial Revolution possible. And believe me, it is still evolving today. Okay, so every story has a beginning, and for steel, that story begins deep in the Earth's crust. Now, before we can even dream of getting to steel, we first have to create its parent material, iron. And that process, well, it's nothing short of elemental. To make iron, you basically need a three-part recipe. First up, iron ore. This is the rock that actually has the iron locked inside it. Second, you need something called coke, which is this super carbon-rich fuel made from coal. It does two things. It provides the insane heat we need, but crucially, it also kicks off the chemical reaction that rips the iron away from the oxygen in the ore. And finally, limestone. You can think of this as the purifier. Its whole job is to grab all the unwanted gunk and impurities from the mix. So you take those three ingredients and you dump them, or charge them, as they say, into the top of this massive 10-story tall blast furnace. Then you blast superheated air in from the bottom, which jacks the temperature up to a mind-boggling 1,650 degrees Celsius. This inferno melts absolutely everything, letting all those chemical reactions happen. After 4 or 5 hours, the pure molten iron sinks to the bottom, where it's tapped off. And what comes out of that process is our first product, pig iron. But hold on, this is not steel yet, not even close. This stuff is a really raw, carbon-rich iron. We're talking about 4% carbon, which actually makes it super brittle. So it's a really important first step, but it definitely needs some serious refining before it can become the hero of our story. And this next part, refining into steel, this is where our raw pig iron gets its superhero upgrade. We're about to see it transform from this brittle, impure material into the strong, versatile metal we all know and love as steel. You see, making steel is all about two things: purification and precision. The main goal here is to get that high carbon content way down, from around 4% to less than 2%, and to kick out all the other unwanted elements. It's kind of like being a master chef, but your ingredients are molten metals, and your oven is thousands of degrees hot. You have to get that recipe just right. And this is the kitchen where all the magic happens. It's called the basic oxygen furnace, or BOTH for short, and it is the workhorse of modern steelmaking. They pour in the molten pig iron, add in some scrap steel, and then they blast pure oxygen into the mix at supersonic speeds. This oxygen causes this fiery, violent reaction that burns off the extra carbon and other junk, and it can refine 200 tons of steel in less than an hour. It's incredible. Hey, remember that limestone we added way back in the blast furnace? Well, here's its big moment. As all those impurities burn off, they get captured and form this layer on top called slag. It's lighter than the molten steel, so it conveniently just floats right on top. The best way to think about it is like the foam on a soup. You just skim it right off to get to the pure steel underneath. Pretty clever. Okay, so we've cooked up a perfect batch of pure liquid steel. But, a puddle of liquid metal isn't very useful for building a skyscraper or a car, right? So the next step is to give it a solid shape that we can actually work with. Now, for a really long time, making solid steel was a slow, clunky process. You'd pour it into these massive individual molds called ingots. The problem was, this often led to defects and was super inefficient. But then came this revolutionary idea: continuous casting.
Instead of separate molds, you pour the molten steel in one long, continuous strand, which solidifies as it moves.
And I have to tell you, this wasn't just some small improvement. It was a total game changer. Continuous casting meant you got higher quality, more uniform steel, and you could make it way faster and much, much cheaper. It's honestly one of the main reasons that the steel in everything from your car to your fridge is so affordable today.
All right, so we've made pure steel, and we've given it a basic shape. But here's where the story gets really fascinating. Because steel, well, it isn't just one thing. It's actually a massive family of materials, and each one has its own unique recipe and its own special purpose.
Not even close. While iron and carbon are the main two ingredients, modern steelmaking is like advanced alchemy. They add a whole menu of other elements, things like chromium, nickel, manganese, to create these custom alloys with very, very specific properties. But the most fundamental trade-off in steel all comes down to carbon. It's like a seesaw. The more carbon you add, the harder and stronger the steel gets, which is great for something like a knife blade. But you lose what's called ductility, which is just its ability to bend or be shaped without breaking. A low-carbon steel is softer and way more ductile, which is perfect for something like a car's body panels that need to be stamped into complex shapes. But that classic trade-off presents a huge problem for the modern world. Think about today's cars. We need steel that is unbelievably strong to protect us in a crash, but at the same time, we need it to be lightweight to improve fuel efficiency. So how on earth do you get the best of both worlds? Well, the answer is basically metallurgical magic. Scientists developed what are called advanced high-strength steels, or AHSS. And this isn't just about adding a pinch of this or that anymore. We're talking about creating complex, custom-designed microstructures inside the steel itself. Over the years, we've seen new generations of these steels, each one pushing the boundaries, leading to the third-gen steels we're seeing now that are somehow both incredibly strong and easier to form into shapes. And here it is. This is the final payoff of that whole amazing journey. We are right back where we started. The car. In a modern car's frame, each one of those colors represents a different type of steel. The ultra-high-strength stuff is used to create a safety cage around the passengers. The softer, more formable steels are used for the outer panels. It is a symphony of materials, where every single part has been engineered with a specific recipe for a specific job, all to keep you safe while saving gas. So, from a simple rock in the ground through fire and chemistry to a complex engineered material that's constantly being reinvented to solve our biggest challenges, yeah, the story of steel is far from over. Which leaves you with a pretty cool question, right? If this is what we can do with it today, what are we going to build with it tomorrow?